Okay, today we're going to start with basically a review of Calc 3 stuff, and typically it's actually before Calc 3. We're going to review dot product, but we're going to be looking at it from a slightly different point of view. Because in Calc 3, when you're doing dot product, and then later cross product, you're looking at it for very specific applications, primarily in 3 dimensions, right? Well, the thing is dot product is not reserved for just 3 dimensions. In fact, the majority, in a mathematical setting, you use it in higher dimensions all the time. In statistics, you use things all the time in higher dimensions. You're not limited. In physics, you're limited to 3D because we live in a 3D world, and that just makes sense. Okay? So we're going to look at dot product, look at all the applications of it for what we want, and then we're going to go further and basically take dot product and see if we can extend that to anything in a vector space. In other words, not necessarily vectors. And that's kind of cool. It's kind of crazy. And it opens up a whole bunch of other things by the result. So let's take vector u and vector v in Rn. Okay? So obviously then vector u would be something of this form. And then vector v, this form. Now, by the way, the in Rn is important because we end the course by looking at vectors that have complex components. So that would be in Cn. And the definition of dot product actually gets tweaked. Our definition of dot product that we're going to use only applies to real valued vectors, which for our practical purposes is fine. Right? That's all we're doing now. But later when we allow complex numbers, okay? So, for real valued vectors, u dot v is defined as, if you were in my Calc 3, we did the exact same way. This is the definition, that's it. Okay? So, what does that look like? That looks like u1 v1 plus u2 v2 plus un vn. It's a sum of the products of every corresponding component. This is why the 2 vectors originally have to be the same dimension, so that they match. Not that dissimilar to matrix multiplication, right? Dimensions have to match, or I won't be able to do this. That's it. That's a simple definition. And again, a lot of what I'm going to do, we did in detail in Calc 3. And since all of you are either in or have had Calc 3, this isn't new stuff, but we're going to take it into places that you haven't gone. Now, because these vectors are in Rn, then all of my components must be real numbers. They are not variables. These are only scalars that we're dealing with here. Can you talk about dot product with functions? Can I have functions there instead of vectors? Yeah, in Calc 3 we're going to be doing things with functions there. But at some point we always evaluate those functions, don't we? For those of you who remember tangential and normal components of acceleration, right? There were some shortcuts where you used, you remember v dot a and v cross a over magnitude of v, stuff like that? Well, the v and the a were vectors of functions, but you evaluated them first and then you performed those, so you got scalars. Yeah, you can actually have vectors of functions, but for our practical purposes, these are all going to be scalars because they need to be linear. Otherwise, we don't have the problem. We don't have the linearity part. Is this true?
Yes.
Why?
Real number multiplication is commutative.
Perfect answer. Real number multiplication is commutative. And that is huge because when we get to the complex vectors, things get tweaked because of the complex part. Well, why is this important? There's your formal proof that dot product is commutative. Is there a tendency in math that we assume commutativity? We just always assume it applies to things? Because when we're dealing with numbers, right? Addition's commutative, multiplication's commutative. Of course, exponentiation, subtraction, division, those are all commutative, right? A to the b equals b to the a. A divided by b equals b divided by a minus b. Oh, actually, no. Commutativity actually almost never happens. Multiplication and addition are commutative. Dot product's commutative. Derivative of a product, but that's still product. Derivative of a sum, but that's still sum. Outside of sum and product, I think you'd be hard pressed to find anything else in mathematics that was actually commutative in general. Yeah, commutativity is actually quite rare. We know that from matrix multiplication. Cross product, is it commutative? For those who remember cross product? No, oh, right? Quotient rule, no. F of G, G of F, no. No, so commutativity is huge when you got it. So that just means it doesn't matter what order I do the dot product. And dot product is actually really big in this class. So we start with that. Now, I want to remind you that what is the algebraic interpretation and the thing involving magnitudes and all that? Well, then we need to first define things like magnitude. Again, we're only dealing with real valued stuff, lest we forget. So let me draw a two-dimensional picture. So let's call this, this is vector v, and let's say vector v is this vector. Then that means the terminal point of my vector is the point a comma b. And this is why a lot of folks get confused about when it comes to not just notation, but the algebra. There is no algebra of points. You cannot add points. You can't do anything with points. Points don't have magnitude or direction or even units, but vectors do. But the terminal point of a vector is a point in this case, because I need to know where it stops. But the vector is the whole thing. So if I ask how long is this vector, that's the same as asking what's the magnitude. Now in this class, we are primarily dealing with unitless vectors. That's extremely artificial, we know that. And I remind folks, in a math context, a lot of the math we do is actually artificial from that standpoint. Go back to baby algebra, XY plane, I drew a graph. Okay, everybody knows that. And then I find the slope of my graph, all that stuff, that was so darn easy. I would be hard pressed to come up with a scenario of a graph that was unitless. I don't think it actually exists. Yeah, you can draw a picture and not put units. But the x has to represent something, the y has to represent something, which means that slope is always a rate of change. Slope always has units. In fact, to say slope doesn't have units means it's probably not slope, it's something else. Slope is the y units over the x units, miles per hour, right? Dollars per gallon, whatever you want to call it. And we sometimes forget that because in the math sense, we were just trying to get the line correct. We were trying to get the value of the slope correct, but we forget the units. Now we get to physics. What happens if you forget the units? Anybody know what happens when you forget the units? Yeah, you don't get any credit whatsoever. I remember my daughter when she took Physics 195, I won't say from which professor, on their first quiz, they were given unitless problems. And then they did it, and she worked so hard. And she got every answer perfect and got 0, as did half the class. The half the class that was repeating the course because they'd failed it the previous semester, they all got it right. Because the instructor wanted the word units after every number, even though every question was unitless. And dimension was not. So it was like the answer is 3, no, 3 units. Which I found to be utterly silly, but the instructor was making a point. And my daughter never forgot units ever again, and neither did anyone else, and that was the whole point. Probably should have said, hey, there's no such thing as a unitless answer, and that might have helped. But if I said, multiply 3 times 4, and you say it's 12, wrong, it's 12 units. No, it's not, it's 12. There's no units implied. Yeah, I found that to be a little silly, but I got the point. We're going to be doing strictly unitless vectors because we're just looking at the algebra of vectors and things in their dimensions. But as you know from calculus, and you're certainly going to learn later if you don't already know this, most of the time a vector in calculus is going to represent something. I mean, what does it represent most of the time? Anybody know? In most of the applications, and again, if you're in Calc 3, you haven't gotten there yet, and you're going to get there soon. Most of the time your vectors represent force. And then you're dotting them with a position vector, which represents distance. And therefore, what's your answer almost in every conceivable problem in Calc 3? Work. Yeah, there isn't any other answer to even consider. But they don't tell you that while you're going because they're not giving you units in the problem. And then later you realize, oh, that's what it is because that's what I'm doing in physics. We're doing literally unitless problems here so we understand the algebra. But in real life, there's no such thing as a unitless problem. Now, I mentioned rate because I want to make sure everybody understands. I go through this in Calc 1 and I do it again in Calc 3. Whenever you have a quotient of quantities involving units, you have a rate. What if the units are the same? That's the definition of percent. Percent is a rate where the units are the same. That's why the answer to a percent is always unitless, because the units cancel. Now think about this. I use 10 gallons of gas to go 100 miles. I can give you units. I've driven 80 of my 100 miles so far on my trip. It's 80 over 100 miles per mile. So it's 80 over 100, or 80% of the trip. That's what a percent is. It's a rate with the same units. Rate, we have different units. And without units, a lot of the math we're doing doesn't make a lot of sense. We're going unitless for now. So when I ask for magnitude, a lot of people will say, well, isn't magnitude and absolute value the same thing? Actually, no. In no context is magnitude the same as absolute value. And I have to point that out because in Calc 3, I have to hit people over the head with a blunt object, because every time I ask for magnitude, they give me an absolute value. Absolute value is unitless. Absolutely unitless. Magnitude of a vector has to have units. It's impossible for the magnitude of a vector to be unitless. If we're talking about force, then the magnitude of a vector was probably measured in newtons or pounds or something. Can magnitude have distance? Yeah, a lot of people say magnitude is distance. It's the length of the vector with the proper units applied. So if I ask for the magnitude of v, what is that? I know you guys all know this. What is that?
Square root of a squared.
Yeah, it's basically, if I make a right triangle, it's the hypotenuse of a right triangle. In reality, this has to have units, whatever it is. And it's, by the way, in a Calc 3 situation, it's usually force. Okay? But we're going unitless right now. But magnitude has units. Absolute value does not have units. In fact, people don't understand. Absolute value's definition applies to complex numbers. It's how far is a complex number from the origin on the complex plane. It's just you're always dealing with 0 in the complex part, so you're looking at a number line. But the definition is actually for complex numbers. There's no magnitude, there's no vector, there's no direction. They're not even from the same universe. So every time someone tries to give me that argument, they're the same thing, I'm thinking, I'm so sorry. I feel so bad for them because somebody deceived them somewhere along the line to even equate the two. No. That'd be like saying in general, well, derivatives and integrals are always the same answer. No, and they're not even the same units either. Yeah, so we know what a magnitude is, and then further, so I say, I need you to go that way. How far is that way? My Calc 3, you know exactly how far it is. That way is infinite, isn't it? Oh, that's not helpful. I need you to go that way 100 feet. So what do? We take that way, we make that way length 1, and then we take that vector and multiply it by 100, don't we? So what do we do first? We make it into a unit vector. So the unit vector in the direction of v is this. And it's a very practical thing. We're going to be using this today. A unit vector is now a direction where the magnitude isn't relevant. So if I said go that way can be any length but applied to a vector of length 1. So the direction is the main thing. So I remind us, in case we forgot, unit vectors are extremely important. Now, there's two things that I utterly hate in life when it comes to mathematics that people and even textbook authors do. In calculus, authors will do things like this. To me, this is scratching a chalkboard with metal claws. This has absolutely no meaning mathematically. Do you know why? And by the way, a lot of you taught that was okay. No, this is not okay. I just made du a quantity. No. Du is an instruction. It is attached to the integral symbol, and that's called the integrand. This is not a quantity. Because it's an absolute mathematical statement. If this is valid, then this equals this. There is no exception. This algebraically is equal to this, which is not even similar to this ever. Why? Because a over b equals a times 1 over b equals 1 over b times a is always true for anything that can be written as a quotient. Your instruction to integrate with respect to u cannot appear in the integrand because you just made it a quantity. Does everybody understand that? This is horrific. This is gross mathematics because it means I can put it in front. Algebraically, these are exactly the same, but from a calculus standpoint, they're not even remotely similar. Well, guess what I see most calculus students do at some point? Now, if you're my class, right, you might be missing a fingertip from doing that one. This is as bad or worse than this one. That's an absolute mathematical statement. If A over B exists, then what must also exist? Without exception. There is no such thing as an exception to numerator and denominator. Anything algebraically that can appear in a quotient can appear in either numerator or denominator, including 0. Because 0 in the denominator just means you're undefined. You just can't finish it. There is no such thing as a restriction on numerators and denominators. Now, if you're taking something that's not the number 0, if this exists, then so does magnitude of v divided by v. In fact, if this exists, then so does the reciprocal of v. We know that's not true. We know that's not even ballpark. That's why you can't put a vector in a quotient, because vector has exactly 2 operations. Addition, scalar multiplication, and that is it. Can you raise a vector to a power? Can you take the sign of a vector? Can you put a vector in an exponent? No, we know there isn't any algebraic thing I can ever do to a vector. I can add them, I can multiply them by scalars. So then why do all calculus students want to put them in a quotient? Oh my goodness. And by the way, I have never gotten through a Calc 3 class without somebody putting a vector in a denominator at some point. It always happens. Because if I can do that, then why can't I put it in a denominator? Actually, you're right. If you can do that, absolutely you can put it in the denominator. And then when I multiply those reciprocals, I get the number 1. Except that none of these things can be done, so just don't do that. This is just, these are the 2 things that make me the craziest. Because I'm a math person. And if you write something that's not true, you can keep going in that direction and get even weirder stuff. Now, let's go back to the simple algebra of dot product, because I want to remind you of something, because we're going to use this to piggyback on other things. All right, I'm going to do 2-dimensional stuff because I can draw the picture. Okay? You've all seen this. You're in my class, you probably could do this for me. There's a relationship between A, B, C, and theta. What's it called?
Law of cosine?
The law of cosines, good. Not the law of sines. The law of sines is very limited because depending on whether you're an acute or an obtuse angle, I might not be able to do things. No restrictions on law of cosines. Theta can be any angle, including the right angle. If you don't remember, c squared is a squared plus b squared minus 2ab cos theta. What if theta is 90 degrees?
Cosine 0.
Then what do we get? We get the Pythagorean theorem as a special case of law of cosines. Is that a good thing? Well, that's more of a, yeah, it's a really good thing. If theta is 90 degrees, then that's 0, I get Pythagorean theorem. So Pythagorean theorem doesn't contradict law of cosines. So law of cosines tells me this relationship. So what I want to do is I want to make this a vector. I want to make this a vector. I want this to be, it doesn't matter which way, let's say vector u, and that's vector v, then this would be the magnitude of vector u, and this would be the magnitude of vector v. The question is, what is this? Well, I know that vectors are physical objects. If I took vector u, and I took the negative of vector u, for example, wouldn't the negative of vector u be that guy right there? Now, what if I took the negative of vector u, and I added it on to vector v? Wouldn't I get that? Did I just do that? Yeah, I think I just did that correctly. It's not a very good picture, I know. Does that look about right? If I took the negative of vector u and I did this, then, probably a little longer, then what is this vector here? See. Well, wouldn't this vector here be v minus u then? Again, v, the negative of u, I get that vector. Whoa, by the way, anytime you're working with vectors and the negatives, you're always going to get a parallelogram.
Shouldn't it be v plus negative u?
Yes, it's the same thing. You can think of linear combination. Plus negative 1 or minus 1. Yeah, if I really want to get strict, but if you want to use a negative coefficient, we don't just plus the negative number. You guys just did. You beautifully wrote linear combinations of a vector recently, right, to give me an answer. Now, why is that important? That means in vector form, oh, this is simply v minus u. So what is the length c? That would be the magnitude. Now, why is that important? Because I can put these magnitudes into the law of cosines. And what would I get? I get the magnitude of v minus u equals the magnitude of u squared, squared, plus the magnitude of v squared minus 2 times magnitude u times magnitude v times the cosine of the angle between them. This is an absolute. I'm giving you a two-dimensional picture, but this would be true in any dimension. I just can't draw it in any dimension. Because I can have vectors in every dimension, and the sums and products and scalar multiples, the definition doesn't change, just the number of components change. Now going back to this guy, sometimes this is referred to as d u comma v. It wouldn't change if I said v comma u. Sometimes people write it that way for this, which by the way is also equal to this, isn't it? If I had subtracted in the other direction, I would have the vector going this way, but the magnitude would be the same, agreed? Sometimes people use this notation. This stands for distance or difference. Some people call it the distance formula or the difference formula. It doesn't matter. It's the magnitude of that difference. So the magnitude of that difference then technically is the distance between the endpoints. That's why I don't care if you say difference or distance. You will sometimes see this notation instead of this. I just want to make sure you understand that these say the same thing. So I would like to manipulate this. I'm going to do it in 2 dimensions and then show you that it's true in n dimensions. This is one of those times where all dimensions give the same results. I just can't draw a picture in every dimension. So if I'm calling vector u u1, u2, and I'm calling vector v v1, v2, then what is vector v minus u? Or, exactly, v plus -1 times u. Won't that be v1 minus u1, comma, v2 minus u2? Isn't that what I would get? Okay. So let's find the magnitude of this squared. So that would be v1 minus u1 squared plus v2 minus u2 squared. And supposedly, it's supposed to equal the magnitude of u squared, which would be u1 squared plus u2 squared, plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times the cosine of theta. Okay? Let's see if we can clean this up. That's what it's supposed to be. I don't know what to do with that. Let's multiply this out. That would be v1 squared minus 2u1 v1 plus u1 squared plus v2 squared minus 2u2 v2 plus u2 squared. That's the left side. Huh. We have some same terms, don't we? Why don't I... Now, what have I got left in my equation? I've got -2 times u1 v1 plus u2 v2 equals -2 times length u, length v, cos theta, don't I? Well, I think it's safe to say we can get rid of the -2. So now it looks like I have u1 v1 plus u2 v2 equals magnitude, cos. Okay. Now, let me stop there for a moment. What if my vectors were in R3? I'm just going to do R3. What if my vectors were in R3? Then wouldn't I have a v3 minus u3 term about right there? Do you all agree with that? Then what would I have here? I'd have a v3 minus u3 squared, and over here I'd have a u3 squared, and I'd have a v3 squared. And then after I squared everything, I'd still have a -2 u3 v3 after the squares canceled, correct? So I'd have this, and then a u3 v3. And the right side would still be the same. If I have a 4th term, then I'm going to have a u4 v4. 5th term, a u5 v5, because everything else is canceled. You with me? What is this quantity?
U dot v.
This is u dot v. And this is the formula you all know and love. This is the alternate formula for dot product. And I say this is probably, certainly in terms of physics, the far more useful one. You say, why can it be more useful? So I always remind people, most of you have been in my class, or are in my class, when you go outside, and I say, okay, I need you to take this vector and dot it with this vector, and when you go outside and you go, okay, where's the x, y, z axes? Because when you go outside, of course, everybody can see the z-axis. This is right out here, right? And you can find the x-axis on the ground. So when I give you the vectors in this form, you can find them outside. Or is it more likely go this way this far and go that way this far and do the dot product? In other words, in reality, you never work with vectors in this form. You work with magnitude and direction. When the plane is flying in the air, I always love this because planes use vectors all the time. So when the plane's flying, I know every time I fly, I can clearly see the z-axis. You guys can all see it, right? And you see the notches on it, and you're like, wow, 30,000 feet. Wow, I can see it right there. Or no? See, in real life, this is what you actually use because you're only dealing with magnitudes and directions. So we kind of need a way of going back and forth.
What is theta in higher dimensions? Like above?
It's still the same theta, I just can't physically measure it. Because remember, your vectors being linear, even in higher dimensions, they're still linear. So it's still the angle between them. It's just that our minds can't comprehend fourth dimension. But think of it this way. You can think 3D in this classroom. Okay? The cartoon character on the screen can only think 2D. But their angle in 2D and our angle in 3D is still the same angle between the vectors, even though they can't see the 3D angle. Or did I just totally mess your brain up by that? So the angle between two 4-dimensional or two 5-dimensional, it's still the same angle because they're still linear. We just can't conceptualize what it physically looks like, but it's still the angle. Crazy, okay? So we know this. This is a very powerful statement. But not only that, I can measure the angle between any two vectors, plus I can also determine when any two vectors are orthogonal. Orthogonal meaning in this context what? Orthogonal meaning, what's another word for orthogonal in this context? Perpendicular. Yeah, in vector sense, orthogonal is the same as perpendicular. Right? I don't have any surfaces. In Calc 3, we're dealing with surfaces all the time. So orthogonal, right, we're talking about then perpendicular to a tangent plane or something. But here, everything really is straight. So orthogonal and perpendicular in this context are the same thing. I can easily figure out if two vectors are orthogonal in any dimension. Is their dot product 0 or it's not 0? Wait a minute, why would it have to be 0? Because cos theta is equal to u dot v over the product of the magnitudes. I'm assuming my vectors are not 0 vectors. So if the angle between them is 90 degrees, then I must get a dot product of 0. Oh, okay, that's a wonderful check. Now, I know we all know this stuff. That's not the thing. The thing is the next thing. The next thing is by far the most important application of vectors, period. Way more important than cross product. Cross product is the most important vector application in physics. If you study math the rest of your life, other than when I introduced cross product for 10 minutes in this class, you're never going to use cross product again, ever. It doesn't ever come up in a math setting. Why do you suppose it doesn't come up in a math setting?
May not.
Well, yeah, but how many dimensions can we do this in?
Any of them.
What about cross product?
Only 3 dimensions.
Only 3, but math in general. When you get to statistics and you're solving really large matrix problems and doing things in stats, you're dealing with multi-dimensions, multi-variables, there's no space for cross product because it's very specific. It only works in 3. And in math in general, we never limit ourselves to dimensions. So comment or? Dude.
Previously, we wrote like v vector and then like 1 over the magnitude of v vector. But
But the dot product is a scalar. Good question. This is a scalar divided by a scalar. So no, I'm not doing a vector division. I'm doing dot product, scalar equals scalar. So to solve for cos theta, these are still both just scalars. Neither one of them are vectors. But we're going to have something that looks kind of like that in a moment. So this is one of my favorites to work with because it's so useful, and we're going to do so much of this over the next week or two. I have 2 vectors. Doesn't matter which one's which. Let's call this one vector v, and let's call this one, how about vector u? Okay? Now, the main application of dot product, hopefully you guys remember, because you probably did this in Calc 2, I have a refrigerator, I want to push it across the room. Let's say the refrigerator weighs 200 pounds and I'm going to push it 50 feet. So how much work do I get done pushing it across the room? You'd say 200 times 50, so 10,000 foot-pounds or pound-feet. I want to push it across the room, but maybe the room's angled, so I end up pushing it that way 50 feet. So how much work did I get done pushing it across the room? Do I still get the same 10,000? Why not? Well, an easy way to think about it, I pushed it 50 feet, so I end up basically where Dominic is. So let me project it straight across to the line I was traveling on, and it's going to be way less than 50 feet. In fact, how much less than 50 feet? Probably like a cosine of theta in there somewhere, isn't there? Oh, so I went 50 feet that way, but how much did I go this way? It's definitely a SOHCAHTOA. All right, I want to push that refrigerator across the room, and I went sideways 50 feet. So how much work did I get done pushing it across? Zero. I'm no closer to the other side. Can I get zero work done even though I did something? Yeah, because I'm in a 90-degree angle, and my favorite is, you've all seen people try to do this. This is awesome. Somebody ran out of gas or something, and okay, I'm gonna release the e-brake, and you're standing behind the cars. It's slightly uphill. That's one of my all-time favorites. And then it starts rolling backwards, and of course, rolls into their car, and then I don't know what people are thinking, but you're not pushing the car uphill. Not with your friends sitting behind the driver's wheel and you're back there. But I want to move the refrigerator across the room and I start rolling backwards. How much work did I get done across the room?
Negative.
I got a negative amount of work done. How could that be? You say, well, the mathematics gives me a negative number. No, it's easier than that. I now have to do a positive amount of work just to get back to the starting point. Oh, so I got to do that much work plus, okay, so it's, yeah, I got negative work done. I'm trying to do something in one direction, I go in the other. This is the classic spring problem, and a lot of textbooks even mess this one up. Do you remember the spring problem? You compress or stretch the spring? If you were in my Calc 1 class, that was day one. Compress or stretch the spring, and they always give you a negative value for work. No, if I'm compressing the spring, I'm getting a positive amount of work done. But the spring is getting a negative amount of work done because it's pushing the other way. When I stretch the spring, it's getting a negative amount of work done because it's pulling the other way. So you got a positive amount of work, the spring got the exact opposite, because one of Newton's laws says, for every action...
Equal and opposite reaction.
Yeah, that's so vague. It's actually for every force, there's a force of equal magnitude in the opposite direction. I wish that they'd say it that way. A reaction is neither equal, right? A reaction is not a number, right? It's not so, no, it's force. That's what we're talking about. So I would like to know, I'm pushing the refrigerator, I went this way. How much did I get done in this way? How much of U is in the direction of V? Here's what I want to do. And by the way, the projection has to be orthogonal. It cannot be anything else but orthogonal. That's why when I'm at right angle, I got no work done. What if the angle is 0? Oh, okay, so let's say that's theta. I want this vector right here. Everybody say that, sorry, there's a right angle. Let me make it over here. I want this vector right here. We're going to call that vector, we're going to give it a name. That vector is called the projection of U onto V. And it does matter what order I write things. I'm projecting onto V, so V becomes the subscript. A lot of people get these backwards. And if I get them backwards, then I basically took this vector and went that way. That's not the same vector, is it? Completely different vector, completely different direction. Okay, I want this vector. Well, let's start with the magnitude. What would the magnitude of this vector be? What is this length? Well, this is very SOHCAHTOA, isn't it? Isn't the length of this vector magnitude U? By the way, does the length of V matter at all in this problem? If I said push the refrigerator across the room, but across the room is forever, but I only want you to go this far. Right, if I said across the room, does across the room ever end? I mean, the other side of the building is still across the room. Yeah, across the room is a direction, but I said 50 feet. Oh, okay. V could go forever, but I want this long. Do you see a SOHCAHTOA here? So I'm looking for this length here. So cos theta is this over this, this would be my hypotenuse. So would you say magnitude U cos theta? Does everybody agree with that? That's exactly what it is. Okay, get rid of all this. Well, I now have the magnitude. What direction do I want to set it in? I want to send it in this direction, so what do? We make a unit vector in this direction. So what would that unit vector be? It'd be 1 over magnitude of v times vector v. This is the direction I want to go. How far do I want to go? This far. Okay? I'm running out of sides here. I'm going to write it right here. There we go. This is equal to the vector that I'm interested in. It's the projection of u onto vector v. There's only one thing I really don't like about this answer. I gave you vector u and v. I'm out in space, I give you vector u and v. I don't know the angle. So it looks like I'm going to have to figure out the angle, huh? Okay, well, let me kind of clean that up. So right now we've got the answer is length u cos theta over length v times vector v. So going back to Duke's statement, right? This is a scalar times vector v. Gosh, if only... oh my God, everyone, turn around. It's Elvis. I'm positive it's him this time. Oh, and it's Professor Mona. I always get that one. I always get him confused. Oh, wow. Look, my numerator. What's my numerator? It's the dot product. Oh my gosh. Can I do that? Yes. We just found the easy way to do this. At no point do you even care what theta is. What's my numerator? What's my denominator? V dot V. You guys remember that from Calc 3? Oh, when you do a dot product of a vector with itself, you get the square of the magnitude. That's an absolute. This is far and away the most commonly used application of dot product. By far, it's not even close. This is called the projection. The work problem is a really cool application that's a really specific application to physics, but this has nothing to do with work. This is in every dimension. The projection of one vector onto another, meaning how much of this vector is going in this direction? I want that piece of vector. By the way, what if v was really, really short? Would it make any difference?
No.
Or am I still getting very specifically that vector? Yeah, because when I make it into a unit vector, I'm going to get this unit vector regardless of how long v is. The unit vector will still be a vector of length 1 in the direction of v, regardless whether v is 1,000,000 miles or 1,000,000th of a mile. Kind of cool. So it turns out we're going to use this a lot. In fact, next day we are going to go over one of the most important algorithms that you're ever going to learn with vectors, the Gram-Schmidt process. I'm not going to say anything about it today. It's the entire lecture next day. We have enough time. But this gives me a vector. Now, I got this vector right here, okay? Just kind of as a strange thing. We're going to do this next day, but I would like to create a vector, just for fun, I want to create a vector that's orthogonal to this one. What if I took this vector and I did that? Notice I'm adding the negative of the vector. What do you think about this vector and this vector? Yeah, I'm going to leave it like that because that's sort of the foundation, the start of next day's lecture. I'm going to create a new vector. Well, isn't the first vector created? Yeah, but it's a multiple of v. But I'm going to create literally a whole nother vector. And then if I give you lots of vectors, we're going to create lots of vectors. And depending on what dimension we're in, we're creating lots of things. So this is projection. Interesting, cool. We have no application for it yet.
Is this going to be used to make the a basis?
Yes.
Okay.
We'll leave it alone because Yeah, this is one of the rare times this semester where the entire lecture is going to be one section. It's big. It's not that it's hard. There's just a lot going on, and we're going to do things in different dimensions. It's cool. Okay, it's cool. There may be things cooler, but not for a little while. All right. So that's projection. We know what dot product is. The whole point of doing the dot product was to get to this point, because then we're going to use this for the higher level things. Now, dot product has some very important properties. Okay? We already said one of them was it was commutative. Okay? So just in general, let's take U and V and Rn. Okay. We know that U dotted with V equals V dotted with V. Okay, that's important. But what other kind of things can I do? For example, if I took U and I dotted it with V plus W, somebody throw in a W here, just for fun. Okay. I definitely want to be defined here. You may have done this in another class. You know, I have V1, V2, V3, so on, plus W1, W2, W3. So I have a new vector of V1 plus W1, V2 plus W2, yada, yada, yada. Now I'm doing the dot product. This is actually a trivial thing to show. Dot product is distributive. By the way, my answer is a scalar, isn't it? Here's one that I'd love to throw in there because people get this one confused all the time. What do you think?
Oh no.
What is wrong with this? I've basically written the associative property. What's wrong with this?
You're dotting a vector with a scalar.
This is a vector dotted with a scalar. That has no meaning mathematically. And no, it's not the same as saying a scalar multiple. No, and actually that dot means dot product. And over here, I have a dot product, which is a scalar, and a scalar dotted with the vector again. This doesn't make any sense. So there's no associative property. Isn't that crazy? When in your life have you seen commutativity apply but not associativity? Well, that's pretty much the only place. So there's no associativity because I'm not a dot product. How about closure? We talk about closure. Now, closure means if I combine two elements of a set using a particular operation, my result is still in the set. I'm taking two vectors in Rn and I'm combining them using dot product. Is dot product closed?
No.
No, I'm not getting a vector back again. Okay, so remember, closure is powerful, but it's not automatic either. And do people get in trouble here sometimes? Yeah, we just assume everything works so nicely, but I'm throwing that at you just because that's kind of weird. So I know dot product, this is true, this is true. One of the really important ones, and this comes up later a little bit more, the magnitude of a vector must be non-negative. Remember later I said we're going to talk about vectors of complex numbers. And this is one of the reasons we have to tweak the definition, because magnitude has to be a real number, even if your vectors aren't real, crazily enough, the way we define magnitude. But if I'm dealing with real valued vectors, would you say that's a piece of cake? Because what I'm doing is I'm taking the square root of a sum of squares. IFF, what does that mean?
If and only
If and only if. It represents a biconditional. If A, then B. If B, then A, if and only if B. If and only if what?
the zero vector.
A magnitude is always non-negative. It can only equal 0 if you actually have the 0 vector. The rest of the time, obviously, it's positive. But we put greater than or equal to 0 because we do allow for the fact that it could be the 0 vector. Now, all of these are conveniently written at the beginning of the section, or in the section. We got this one. Yeah, that's pretty much it. Okay, magnitude of V. Oh, and we said this one already. V dotted with V is the magnitude of V squared. That's not really a property. That's just we know that's true because of the way magnitude's computed. At the beginning of chapter 4, section 4.1, we were given 10 axioms that we know apply to all vectors. And it was pretty easy to see, the closure of addition, scalar multiplication, commutativity, associativity, all the stuff. Then we said the Michael Club. If you had a set of things, not vectors, but things that all of those rules applied to, we said, we'll call that thing, that set of things, a vector space. They're not vectors, but they act like vectors, okay? They act like vectors. I know it sounds weird, but we had a cat when I was growing up who thought he was a dog. We had 2 pit bulls, and we had a cat, and the cat would beat up on the pit bulls. The pit bulls were terrified of the cat. The cat had like his sleeves rolled up, he had a little cigarette hanging out. He was the meanest cat you could imagine. You couldn't pet him. You could put your hand out, and he'd ram your hand with his head, but if you tried to pet him, he'd bite you and scratch you. He lived outside, he caught animals. We never actually fed him. He lived on a ranch. We saw him flying off the roof all the time of this little shed trying to catch birds in the air. It was the funniest thing you've ever seen. But this cat thought he was a dog. We'd go for hikes. Cats don't go on hikes. This cat did. So this cat thought he was a dog, so he had all the properties of a dog, so we actually fed the cat in the dog dish with the dogs. Yeah, same thing, right? This cat was the closest thing to an animal vector space you're ever going to see, but he was part of the dog space, literally. So I have a set of things, they act like vectors, great, call them vector space. What if I had a set of things where when combining all these dot product things worked for them? Huh. Let me start with a really simple example. I'm going to, just because I'm bored with dot product is so, 20 minutes ago to us. I'm going to define a new thing, but I'm going to use different notation. I'm going to say U and V, let's keep it simple, they're in R3. I'm going to define a new notation. This is not a vector of vectors. This context means I'm going to define a combination, a way of combining things. Whenever you have, if you're using this notation and you have 2 things here, these 2 things could be matrices. These 2 things could be functions. These 2 things could be vectors. It means I'm going to define a way of combining them. Does that make sense? This is not a vector. V1 plus 4 times U2, V2. I think that thing just beeped.
Just turn it back on.
Okay, good. And plus 7 times U3, V3. Is this dot product? No, I put coefficients there. But think of all of the rules of dot product. Well, first of all, if I change the order of U and V, will I get the same answer? Yeah. If I take the magnitude of this, will I get a non-negative value? Yeah. If I dot this with itself, the properties that I just told you about, all of these will be satisfied. I just gave you basically a version of dot product that is consistent and all the rules of dot product will apply. I just defined it differently, which is totally weird.
Is it supposed to be that U is an element of V?
No. No.
That's what you.
No, thank you, exactly, sorry. Comma, thank you, good catch. U and V are in R3. I put positive coefficients down that weren't ones, but the major things that are true about dot product, like commutativity, how about the distributive property? No, it's still going to work. All of those things will still work. But this isn't dot product. This is what is called an inner product. Dot product is just one version of inner product. Just for fun, could you make up, let's just stick with R3 for a moment. Could you make up all sorts of coefficients here and still have it work? What do you think? If I just started making up coefficients left and right, would this still work?
Yes. Or positive.
I'm sorry?
Positive coefficients.
Oh, wait a minute, what do you mean positive coefficients? What would happen if would anything change if I did that?
No. Oh yeah, that's good. Real coefficients.
Would anything be violated if I did that? Would the magnitude of the vector necessarily be non-negative if I did that? Well, if I said, okay, let me define my U as, let me keep it real simple. My U is 0, 0, 1. then what's the magnitude of u? No, in this context,
Oh, -7.
be -7. Do you see a problem with that? Yeah, so you hit it right. I can put any set of coefficients here as long as they were not negative. Because the negative would fail the magnitude test, wouldn't it? Does everybody see that? If I use this notation, then it's 3 times 0 times 0 plus 4 times 0 times 0 minus 7 times 1 times 1. And that would be negative. So there are certain restrictions. Yes, not anything goes, but isn't that kind of crazy? So then what's dot product if anything I put there that's legal, which basically any positive coefficients would be legal. As long as I put things that are legal, then dot product is just going to get lost in the shuffle. No. It gets its own special name. Dot product, we're now using a new term for it. We know what dot product is, but in the big picture of all the possibilities, it's called the Euclidean inner product. Doesn't that sound important? That's dot product. There's an infinite number of inner products just for vectors alone, but only one of them is actually dot product. That's called the Euclidean inner product, which I find interesting because I think vectors came around several hundred years after Euclid lived. But yeah, it's okay. Who is Euclid? Anybody know? He has a lot of names. One of the terms, he's the father of what? Modern geometry. Yeah, he's credited with a lot of important geometry works. But the most cool stuff are the things that we call non-Euclidean. The most interesting geometry is actually the non-Euclidean, which you haven't had a lot of exposure to, and probably won't really, unless you take the right classes. Does anyone know what non-Euclidean geometry is? Think like warped space, weird things. The idea that if I had a beam of light that was powerful enough, it just kept going forever and ever and ever and ever and ever. In theory, what happens? Anybody know? It comes back around because we believe the universe might be curved in that way. But the easiest way, the closest distance between 2 points we always know is a line segment. Is it always? What if I'm on the surface of a globe? Think of a globe now as a map. I have 2 points, let's say, that are near the equator. Think of a map. Is the shortest distance the line segment? No. Planes will go like this, because it's way shorter. Because now I'm on the surface. That's non-Euclidean geometry. It's cool, it's crazy, don't worry about it. We're not going to do any of it. But the Euclidean inner product, when you hear that term or read that term, that simply means dot product. That's all it means.
Would it be right to say that inner product is a set and Euclidean inner product is a subset?
No, the inner product is an operation.
Operation.
Yeah, I'm defining the inner product of u and v to be that this is the inner product of u and v in my definition. Your definition, you say, no, I want to use different coefficients. So sometimes the instruction might be determine if this is a valid inner product, and we just determined it was not because of the minus sign. Now, probably the most interesting and the most common form of inner product is not applied to vectors. Remember I said, imagine everything that we know about vectors, and we define dot product, and now I loosely define dot product between matrices, or dot product between functions. Now you see I could do this. I'm going to give you a really simple example. Okay? I'm now going to define something. That notation means I'm defining the inner product between A and B. This clearly is not a vector because A and B are not scalars. Okay? I'm going to define this to be, how about A1, B1 plus A2, B2 plus A3, B3 plus A4, B4. That's kind of boring. If you want, you can throw some cool coefficients on there, you know. Zachary's going to throw a pi, Steve's going to throw an e on there, Matthew's going to throw a root 4, and then he realizes later on the root 4 is boring, it's only a 2, you know. Is this a valid inner product? Based on what you just saw, so if I do a magnitude of A with itself, and I do like, okay, and is it going to be commutative? Yeah. Yeah. I basically just defined a way of doing dot product between two matrices.
Well, what is the magnitude in this context?
Magnitude would be, that's a great question. In vector sense, we would say V dotted with V is what? Is the magnitude squared. So therefore, in terms of dot product, how do I get magnitude? I technically have to take the square root of this, wouldn't I? Remember, V dotted with V must be a non-negative number, so I can take its square root. So this would actually be the definition, if you will, in regular vector terms. So what would we do here? We'd say the square root of A1 dot, A1, A1, B1, and so on, or A2, A2, and so on. So I would still say magnitude is the square root of something with itself. So in the simplest sense, if I said, what is the magnitude? You'd say, do this, and then take the square root of your result. That's it. It's because it has to have the same meaning in that sense. The way I calculate it might be different, but the meaning still needs to be the same. Where this is used primarily, believe it or not, is with functions. Functions are the most common use. I'm going to do an example.
It's kind of boring, but can you have a coefficient of 0?
Yeah. Yeah, I mean, yeah. As long as it was non-negative, that's really the thing. Because we just can't run the risk of getting negatives in the answer.
So, like, what happens if A is all positive and B is all negative, and then you've got a negative?
Oh, no, that's okay. It's when something's applied to itself that you can't have negative. Remember, like in vector sense. In vector sense, this has to be non-negative. But just in general, vectors, can U dotted with V dot product, can U dot V be negative? How often is it going to be negative? Half the time, yeah. No, vectors dot product, negative half the time. It can be 0. But U dotted with U can't be negative. That's what we're saying. So this quantity can easily be negative. This quantity cannot. That's the key. Something inner product with itself has to be non-negative. That's why when I threw the negative coefficient, we showed that one would fail. So as long as all my coefficients are positive, we actually are consistent. Now let me show you one of the most common ones of all. F and G are functions. Right? F of x and g of x. Keep it simple. One of the most common inner products, we're going to do it in a moment. This is one of the most common and important types of inner products, the inner product of two functions. Now, the integral can be negative 1 to 1. It can be another, depending on the function, sometimes it's negative infinity to infinity. Negative 1 to 1 is safer. F and G are functions that are defined in that region. Again, it wouldn't make any sense if this was an improper integral. That's not what we're talking about. Okay, we're not talking about, well, f is 1 over x and g is log x. No, this is not defined for that whole part. It's got to actually be defined there. So f and g have to be functions that are continuous from negative 1 to 1. That's the rule. Okay, you have to be able to do the integral. So here's what I want to do. I want to do an integral problem. And by the way, I'm going to ask you this question, but I'm going to keep it really small. Okay? So let's say f of x is 3x plus 2, g of x is x squared minus 1. Let's keep it really simple. Okay. I want to find a few things. One of the things I want to find the inner product of f and g. I want to find the distance from f to g, using the exact same way we defined it with vectors. So I'll walk you through how that works. These are both kind of crazy. Well, the first one says, I want to take the integral from negative 1 to 1 of the product of these two things. Can this answer be negative or 0?
Yes.
Yes, because I have two different functions. Okay. I don't know if it is or not. I haven't done it yet. So let's multiply this out. What would we get? We'd get 3x squared, 3x cubed, sorry, plus 2x squared minus 3x minus 2. This will be the only integration we do all semester. I'm pretty sure you guys could handle this one, right? 3x cubed. All right. So what do I get? Well, if you're lazy like me, you guys remember a trick from Calc 1? Yeah, you can integrate the whole thing. Knock yourself out. That's what I'm gonna do. Why am I gonna do that? 'Cause that one's 0. Why is that 0? Odd function, symmetric limits.
Oh, cool.
You guys remember that? How many know that one? Be honest, how many know? If you're in my class, you know that one, because it's a great shortcut. You can't do that with polynomials. You can only do that even with odd functions. How about this one? Even function symmetric limits, it's 2 times 0 to 1. This is what I do when it's symmetric limits, always. I never integrate the whole thing, I'm too lazy. Plus, I might make mistakes, too much work. Way easier. Okay, so what do we got? We have 2 times 2/3 x cubed minus 2x from 0 to 1, which is 2 times 2/3 minus 2. So what's that? Negative 8/3. Okay, we got a negative number. Don't read anything into the value. I just want to be able to find the value. But now the next one. What did I say this was in vector terms? Wasn't it the magnitude of f minus g? How do you find the magnitude of a vector? You dot it with itself and you then
Square root.
take the square root. So what we're going to do, we're going to find inner product f minus g, f minus g. When we're done, we're going to take the square root. Because technically this would be magnitude squared. Something done on itself is always magnitude squared. Don't put a square root around it. I don't want to put a square root around the integral symbol. That'll just be ugly. Calculate the integral, and then the answer will be, this is not the answer. The answer is the square root of this. But the first thing I need to do is f minus g. So what is f minus g? We'll write it up here. Now this one's not as fun. F minus g would be what?
Negative x squared plus 3x.
Okay, I'll do it in that order. Step, I like it. Yeah, let's do it in descending order. It might be easier. So negative x squared plus 3x
Minus g, so that's plus 3.
plus 3. Okay. Now, next, I need to do f minus g squared because I'm doing it on itself, which means my integrand is going to be this times this. I got to square it. Okay? Do you have a lot of experience squaring cubes in general in math? No. So there's a simple way. All right. So it's x squared, right? So I'm going to have what? X to the 4th. If it helps, you just put them side by side. I'm going to do it the long way, not the way I do it. I'm going to be done in 8 seconds, but I'll lose you all in the dust. It's knowing which terms to combine. That and that and that and that and that and that and that. Okay, let's just do it out the long way.
Oh, right.
So top, and so then I have minus 3x cubed minus 3x squared. Okay, that was x times everything. Now I do 3x times everything, but then move it over 1. So minus 3x cubed plus 9x squared plus 9. Now do the 3 times everything, but move it over 1. Minus 3x squared plus 9x. Did I just lose that? Plus 9. Oh, hold on. Did I do something? Am I seriously? I think I lost something. Hold on. 4 cubed squared x. There we go. And then x squared. Okay, good. Do you notice, by the way, I line things up? Again, I'm lazy. You gotta understand that. So let's see. It's x to the 4th minus 6x cubed plus 3x squared plus 18x plus 9. I now want to integrate that, calculate that value, and then in the end, take the square root of that value. But don't do that all at the same time, one thing at a time. So now let's write it out. The inner product of f minus g and f minus g is the integral from negative 1 to 1 of x to the 4th minus 6x cubed plus 3x squared plus 18x plus 9. Do you have some odd terms in there? Symmetric limits? So now I'm going to be really lazy. I'm not even going to rewrite it. You already know when you rewrite it, the odd terms, that integral is 0, and you're only going to be left with the even terms. So when I rewrite it, can I just rewrite the even terms? That's what I'm going to do. Yeah, I'm lazy. Understanding because An odd function with symmetric limits is always 0. The key is not the odd function. The key is the limits have to be symmetric. If it were -1 to 3, no. There's no trick. You got to do it. But it's -1 to 1. So that and that will disappear if I separate them. So I'm just going to end up with, in fact, I'm going to go a step further. I'm going to go 0 to 1 and double, because that's what I always do with even functions. It's easier. Oh, now I'm really being lazy. I can say with absolute certainty the value of this integral is equal to this. And now I've made it much easier. So now we are 2 times 2/5 x to the 5th plus x cubed plus 9x from 0 to 1. So I'm 2 times 2/5 plus 1 plus 9. So what's that? 104/5?
Is it 1/5?
Did I lose one?
It should be 1/5.
Sorry, which was?
The coefficient of x to the 5th should be 1/5.
Oh, thank you. You know, I did the 2 twice. Thank you. Yes, you're right. 1/5. Good catch. So that's now 51, so that's 102/5. Does that number mean anything to us? No, it's what we got. Now, this is this. This is not the answer. So I'm going to state the answer. The answer is DFG. This is the square of DFG. So what is DFG? Now here's the craziest part. The dot product formula in terms of magnitude still applies. So can I find the angle between the two functions? Sure. How about if I gave you a couple matrices? Can I find the angle between the two matrices? Yes. Don't give it a physical meaning. No. I drew a matrix and I drew another one kind of crooked and I found the angle between. No. It's not that. This is a very, very abstract setting, understand. But we are doing the equivalent of dot product on things that aren't vectors. Is that crazy or what? Now, this has an application. I'm only going to refer to it. We're not going to spend 1 minute on it, because if we spent 1 minute on it, we'd actually have to spend about the next month on it. In like a senior level upper division class, kind of complicated. Turns out what's considered the most important of the inner products in terms of integrals. There's a particular type of integral. The author introduces it at the very end of chapter 5. We're going to look at it, and then we're going to wave at it as we walk by. If you're an upper division engineering student, this would probably be the entire course. I'm not going to try to cover it in 5 minutes, please. But there's something where you're doing an inner product of basically a basis of something. Remember we talked about differential equations having linearly independent solutions, and you're working with these things here. It's an inner product from 0 to 2 pi is the most common one of these horrible things. It's called Fourier analysis. There's an entire branch of mathematics, and if you're unlucky enough to have a course in it, you know, it's not easy stuff. The author just gives you an illusion, just says, hey, check this out, and then please just move on. If you want to study that, great. We're never coming back to it in this class, because I'm just showing you where inner product can be applied to functions, and then we're going to move on. We're not going to spend any time on this. I'm just showing you this as a thing. One of your classes down the road might actually do this. We're going to still concentrate on dot product. I wanted to illustrate you can do the equivalent on dot product on other things. So what have we done today? We did it on vectors with different coefficients. I did it on matrices, and then I just did it on functions. Completely crazy. But the very fact that I could do this goes back to our argument of vector spaces. If a set of things has the same properties as vectors, then a lot of the conclusions I made on vectors I can make on these things. And this is one of them. If I can do dot product on vectors, then I have an equivalent of dot product that I could do on a vector space. And again, I just did it with matrices and functions. Whoa. Now, do we spend a lot of time on that in the big picture of linear algebra? Actually, no. I've taken upper division and graduate linear algebra, and we don't come back to either one of these. You come back to these in other courses, though. Like I said, if you're an engineer, you may come back to this stuff in an engineering course and doing essentially the inner product of integrals to do the Fourier analysis. It's gnarly stuff. Okay? Question?
You might have said it, but what's the D?
Distance or difference in vector terms. Do you remember when I did the law of triangles. And I said, if I think of this as a vector, and this is a vector, and this is a vector, then this is the difference of these two vectors. So in terms of magnitude, if this was u and this was v, what's the magnitude? We say it's the distance between u and v, and therefore that's how long this vector is. And so this, I said, it's kind of universal notation. It equals this in vector world. But now in our world, we'll actually use this symbol because we don't even need to use vectors. It still has the same meaning. It's technically the distance between them using this version of dot product. Does that help? Don't dwell on these. The questions I've asked you are basically this question here. I asked you the same question so that the algebra is really low level. I just want to see you navigate through a process. Okay? By itself, no, it doesn't have any meaning just by itself. It has to be extended and then used in an entire area of mathematics. This is exposure only. Okay? That's all we're doing with this. We keep moving on in this course. Why is it exposure only? Because this is math 254. It's not math, 500 or 600. In other words, this is called intro to linear algebra. See, at every level, you get more stuff. But this is the exposure, not the mastery level. Will you ever reach mastery? Maybe. If you take enough of it, if you're good enough at Calc 1 and 2 and 3, can you master calculus? You can master the execution. Will you necessarily understand why? The theory. Sometimes that comes later, but you can still do everything. The common thing, and a lot of you were in Calc 1 and were studs in Calc 1. You were great in Calc 1. And the response I always get is the same. I knew how to get right answers. Don't ask me to explain what we did. I knew how to do problems correctly. I knew the right way of doing things. I could get right answers. And I could tell you how to do it. But if you ask me why, I don't think I could explain. But I say those same students, when they get through Calc 3, they usually do understand the why now. They've seen it enough, and then now they've seen it from a different point of view. They go, no, we did it. I knew this was the right thing to do, but now I know it's because. So a lot of the becauses have been answered. But there's still some theory that you don't understand because the textbooks don't show it yet. And in the old days, the language was every time they'd present a theorem, they'd give examples of its demonstration. But it would say the proof of this theorem is beyond the scope of the text. That was the universal language. What does that mean? That means if you study math forever, maybe your last semester of your senior year in college as you're getting your degree in mathematics, maybe your first year in grad school, you actually will see the proof of that thing. I saw the proof and development of a determinant in my second graduate linear algebra course. I knew how to take a determinant in 7th grade, but couldn't have told you why. So I gave you guys glimpses. Remember we talked about the rotation of the numbers and all this? That was a glimpse. It's actually way more complicated. But there's stuff going on that explains the why in great detail, but a lot of times we don't need to know the why. We just need to know the how. When you're engineering and you're answering questions, no one's going to ask you to write a proof that your technique is valid. You know your technique is valid, and you're going to do your technique. Right? You don't got to go back and prove it again. Okay.
I was going to ask what you think when textbooks put in the proof is left as an exercise to the reader.
That would mean the proof is not complicated. That's usually what that means. In a discrete math course, one of the most common problems you get when you first start doing proofs is prove the sum of two rational numbers is a rational number, or prove the product of two rational numbers. It's not a complicated proof, but it's a really good one. So what I usually do is I prove one of those two randomly, and then I ask the students to prove the other one. Because it's not complicated, but once you see one of them done, you can do all versions of it, even though it's not the same proof. So I actually like that question if there's been enough explanation that you can navigate through it. So if I ask that question, it's more often not a bonus question. Okay? All right, let's go ahead and click that.